Solid mechanics is the study of how materials react to forces like stretching, bending, and compression. It is important in biomedical engineering to design safe medical devices. Parallel bars are used in physical therapy to help patients walk and balance again. So they must be strong and stable. We choose parallel bars because they are common in rehab. They need to support different user weight safely. So the design must be strong and reliable. In this project, we used SolidWorks to design a simplified parallel bar. We made a 3D model and simulated how it reacts when someone puts weight on it. Our project has three main objectives. First, to understand how the parallel bar behaves under force by studying stress, strain, and deformation. Second, to use SolidWorks to create a 3D model and run simulations under different load conditions. And third, to perform manual calculations and compare them with the simulation results for accuracy. Stress is the internal force in a material when a load is applied. It tells us how much force is acting on a certain area of the bar. The formula is sigma equal to F over A, where sigma is stress in Pascal, F is the force in newtons, and A is the area in squared. Strain, shown by the symbol epsilon, measure how much a material stretches or compresses when stress is applied. It is calculated as the change in length over the original length. Strain has no unit because it's just a ratio. It helps us understand how much the bar deforms under load. Displacement, shown as delta x, is the amount a point moves from its original position when a force is applied. It's a vector quantity, so it has both magnitude and direction, and it is measured in millimeters or meters. In this project, displacement helps us see how much the parallel bar shifts when someone leans or holds onto it during rehab. For this project, we use SolidWorks, a CAD software for 3D modeling and simulation. We designed the full parallel bar, including the handrails, vertical supports, and base. Next, we selected materials from SolidWorks library. The software automatically applies key properties like Young modulus and yield strength. Then, we run simulations to see how the structure reacts to force. The results show us important values like stress, strain, and deformation.
For methodology, I will give steps of designing the parallel bar. First, create the piece by selecting the plane and sketch a rectangle, then extrude walls to create a 3D base. Next, for the pole, sketch a square at the corner of the base and extrude walls to get the height. Repeat the step for the other sides. To create the bar, sketch a circle on the pole and set the desired diameter. In this simulation, we start with 20 cm, then 30 cm, and then 40 cm radius. Extrude it to design a length bar. In assembly, select mirror component and clean to get a second parallel bar. So here is our engineering drawing with the heights and width of the poles is 1000 cm and 100 cm respectively, and the length of the bar is set to 1800 cm and the length of the base is 2000 cm. To observe the mechanical behavior of the parallel bar, analyzing important solid mechanics concepts such as stress, strain, and deformation, we change the diameter of the bar. So the first simulation, we start with 20 cm, and then 30 cm, and then 40 cm.
Greetings, my name is Daniel, and in my part I will explain about the manual calculation. So let's take a look at the known values for the calculation and the assumptions. For Young modulus, this value was chosen based on the standard value for alloy steel, which reflects of its stiffness and resistance to elastic deformation, while for the yield strength, the value is 200 exponent negative 9 Pascal. This value was chosen to represent the stress level at which alloy steel begins to plastically deform. This is a typical conservative value used for a general structural grade alloy steels. By using the information we have just now, we will perform a calculation on 5 elements, starting from the area, the stress, strain, displacement, and max load. After we obtain that information, we will tabulate them in this table. So this table shows the summarized version of it. Now let's look at the free body diagram of our model. Basically, this model adapts the model of actual free body diagram. Perform an analysis based on our manual calculation. So for the first one, we have a stress decrease as radius increase. This means that as stress decrease, a smaller area indicates a higher stress, meaning a larger area contributing to better force distribution. Next, we have a max load capacity is far above 100 Newton, confirming a safe design. A higher radius bar can carry more loads before yielding. And the third part, all bars deform within safe elastic limit. This can be seen in the strain value or in the range of exponent -9, indicating elastic behavior. Next, we have is strain decrease as radius increase. This means that a lower stress indicates lower strain. When the bar stretches, it stretches less under the same load, indicates more stability. Last but not least, displacement reduced significantly. This can be seen in the video of 7.16 to the power of -8 reduces to 1.79 power -8. This value indicates that less deformation equivalent to stiffer structure.
In this simulation, we apply a 100 Newton force vertically on the cylindrical bar to represent a realistic loading condition, such as a person gripping or leaning on it. The objective was to observe three key mechanical responses: one is stress, displacement, and equivalent strain. By analyzing this result, we can evaluate whether the bar design is structurally safe and stable under typical usage conditions. For the parallel bar, we choose alloy steel as the main material due to its excellent strength, stiffness, and durability. It can withstand high loads with minimal bending, making it ideal for supporting body weight during exercises or rehabilitation. Alloy steel also has a fatigue resistance, meaning it can handle repeated use over time without failing. While it's heavier than other materials, its structural reliability outweighs the weight trade-off, especially for fixed installation. For the simulation procedure, for the first step, edit the sketch of the parallel bar to 20 cm radius. Next, open the SolidWorks simulation and click New Study and set it to static. Select the materials of the parallel bar. I chose the alloy steel. For the last three steps, by using fixed geometry function in fixtures, use it at the base and side of the vertical support, and then select the external load and choose the force to be 100 Newton and put the force to the parallel bar. Lastly, run the simulation process and create the report for further analysis of the parallel bar. These are the simulation results we obtained after applying a 100 Newton force to the cylindrical bar with a varying radius of 20, 30, and 40 cm. The maximum stress decreased from 3.54 at 20 to 1.62 at 40 cm. The displacement also dropped significantly along the increase of the radius. Similarly, the strain reduced as the bar radius increased. This clearly shows that a larger bar radius results in better structural performance, with less stress, less bending, and less deformation under the same load. To summarize, the simulation helped us evaluate the effects of different bar radius on stress, displacement, and strain. We found that increasing the radius significantly improves structural performance. However, some factors may affect accuracy, such as software limitation or locking mates used in the assembly, which might not perfectly represent real-world context. Ensuring proper connection and using the latest SolidWorks version can help reduce these issues in further simulation.
As a conclusion, this project applied solid mechanics principle to design and analyze a parallel bar structure. Using both manual calculation and SolidWorks simulation, we confirm that increasing the bar radius improves structural performance. The design is safe, strong, and suitable for rehabilitation, with all results aligning well between theory and simulation. Thank you.